Hello everyone and welcome to our latest installment of Mechanism Talks. Today we're going to talk about the mechanisms for dihydroxylation and epoxide reactions. This is in the addition reaction section. That means we're going to have alkenes and we're going to be adding things to the alkenes. So hopefully you'll find this useful. So in this video we're going to go over 3 different reactions. We are going to go over more in detail about the products of these in class, but we're just going to focus on the mechanisms for this video. So as you can see, for the first reaction, we've got dihydroxylation. So we're adding a syn-diol, that means 2 alcohols, and they're right next to each other. This reaction is a syn addition, which means that both of the OHs should be on the same side, so that's why they're both wedged for this example. For the next reaction, we have epoxidation. The thing on the right that you see, the ring with an O, that's the epoxide. It is a syn addition, so that's why we've got 2 wedges going for the ring. And then the last reaction we have is an SN2 on an epoxide. So it's not technically an oxidation like the first two, but it does involve oxygen, so that's why it's in this section, and it's with epoxides. So as you can see, you're starting with something that's already syn, but then when you add the nucleophile, the final product is going to be anti. Let's get into the mechanistic details for why this stereochemistry occurs. For the first reaction, we're only going to do a partial mechanism. So as you can see, we're going from the double bond to where we add the osmium tetroxide to get the oxygens attached, but then we're going to stop at that intermediate. So for the mechanism, you only need to show it from the beginning to that step. The second step shown on the right is a reaction to remove the metal, the osmium. There's actually several ways that you can do this, but in this case, it's going to do an oxidation of the osmium to remove it. This is really beyond the scope of this section of the material, so we're not going to cover that part in detail because it's more about organometallic chemistry. So now let's get into the organic part of the mechanism, the part where we're going to add the osmium tetroxide. For all the mechanisms in this section, they're very, very short. Like most of them are 1 step except for the last one. It's like 2 steps. So what we're going to do is really focus on how the arrows lead to the bonds. They don't follow a normal pattern like some of the previous things like halogenation or Markovnikov additions. So instead, let's focus on how arrows relate to the bonds that we get in the product. Okay, so I'm going to color code them. Hopefully that will help. So the first thing we need to do is draw the structure of osmium tetroxide. So it looks like this. And then we said in the previous section, we were talking about how all the addition reactions, double bonds are going to be the key nucleophile. So we'll write nucleophile here, and then the electrophile is going to be the osmium tetroxide. Now, normally you'd want to go to the metal part of the electrophile, right? Because that's the most positive. But in this case, if you look at the final structure, that doesn't make sense, right? We don't want to attach anything to the metal. The metal's not attached in the final product, and the oxygens are. So this is going to be slightly different than what you might expect. So instead, we're going to have this go to make a bond with the oxygen, right? Because that's what we're trying to get the bonds on there. So we'll just draw an arrow from the middle of the bond to the O, and that's going to be our first bond we're going to make. So once you do that, if you add that to oxygen right now, it's already got an octet, so we're going to have too many electrons. So to get rid of the electrons, we're going to move this double bond into the osmium tetroxide. Now, this is not something you've seen before, but because it's a metal, it has extra space for electrons. It has empty d orbitals where electrons can go. Lots of metals like to have extra electrons. Some have more than 8. Many have as many as 18. That's a normal thing for them. So in this case, because it's a transition metal, that's why it's allowed to sort of just put the electrons on top of the metal. Okay? So once we know that's happening, we also look at the product and we're trying to get a single bond between the oxygen and the osmium. So to do that, we're going to break this double bond. So since we know we also need to form a bond in the final product, why don't we take that double bond from the osmium double bonded to the O and make that go to the carbon, and that will make the third bond. So then that's our total product. So if I color code it, if you look, this arrow was this color. So now over here, that's the bond it made. Then this arrow was this color, so it didn't really make a bond. Just kind of think of it as a lone pair on that guy. And then if you make the last bond, the double bond here, went to go make that bond there. So if you look at that, I color coded the double bond to make that. Okay? So hopefully that makes sense. Just try it out. It is really short, so if you have to memorize it, at least it's short, but hopefully it can make a little bit of sense as we go. All right? So great. So that's the first one. Already done. All right, so now we're ready for our second mechanism. So this one's for epoxidation. Epoxidation happens when you have this molecule here, which is called mCPBA. It's an abbreviation. It's this molecule over here at the bottom, the blue one. It's called metachloropurbenzoic acid. You don't have to know that name. It is a peroxy acid. A peroxy acid means that instead of being a regular carboxylic acid, right, you notice there's something different. What do you see that's different over here? Right? It's got an extra O. The extra O is like peroxide. An OO bond is found in hydrogen peroxide, so that's peroxy. And then it's a benzoic acid because it's got benzene. And then it's chloro because it's got a chlorine. And then the meta is telling you where the chlorine is on the benzene ring. So that's the structure. So this is going to be another one where it's making a ring on one side, so it's syn, and it all happens in one step. So kind of like when we make the bromonium ion, it's just instead it's with an oxygen, and there's like the arrows are weird. So let's see what it looks like. So we're going to draw out the structure. I'm going to draw it a little fancy just to make the arrows a little bit easier to see. But if we look, we've got the same structure here, right? We've got the benzene, we've got the chlorine, we've got this double bond O, and then there's an O with another O, and then the H. And all those bonds are drawn out on purpose because we're going to break some of those bonds. If you look over here at the byproduct, remember, you don't have to show the byproduct. It's not required, but sometimes if it helps me with the mechanism, I'll try to remember it just because that makes it easier for me. So, because I know a carboxylic acid, I know what that looks like, and I know it's very similar to the starting thing, that sort of helps me. So, if you look, I'm going to have to keep all the main parts, but I'm going to have to take one of the O's off. The O I'm going to take off is actually the one on the end, and then the other O's are going to change. So let's look and see what that looks like. So the first thing is, what's going to be our nucleophile for this reaction? Right? It's going to be the alkene, because alkenes act like nucleophiles. They're not strong, but they are nucleophiles and in addition reactions. So that's going to be my nucleophile. I want to get that oxygen. So remember, I said the oxygen in the product is going to be this oxygen here on the end. So I'm going to have that go straight to the oxygen. So now when I do that, I'm going to have to break a bond, right? Because oxygen already has an octet. So I'm going to take the bond I'm going to break is going to be between the two oxygens. I know that's a weak bond because chemically peroxy bonds are weak bonds between the oxygens. You can measure that thermodynamically. That's why hydrogen peroxide is so reactive. So I'm going to break that bond, and actually that oxygen is going to become the carbonyl of the byproduct. So I'm going to go from the bond to make a carbonyl. Then I have to move the current carbonyl, right, the one that I already had, because that would be too many bonds to carbon, right? That'd be 5 bonds. So I'm going to take the double bond of that side and then draw that to the hydrogen. And that's how I get this OH bond over here. So if you look in the byproduct, we've got an OH over there. And then obviously I can't have 2 bonds of hydrogen, so I need to take that bond. And where do you think that's going to go? The only bond we're still missing is the other side of the epoxide. So we're going to go from the bond there to the carbon. All right? So I know it's got a lot of arrows, but if you can figure out what arrows match with which bonds, it makes it a whole lot easier. And I think knowing the byproduct is helpful for that. So before you move on, I encourage you to pause this video and make sure you can see where each arrow matches each bond. So pause it and check that first. Okay, good. Hopefully you got it. So if you look, we've got this one, the very first one, the blue one, ended up being this one. We didn't know that right away, but it was there, to the oxygen here. And then this one broke this bond to make the double bond. And then this double bond broke to make a single bond, OH. And then this bond broke to make this single bond between the oxygen and the carbon. So hopefully that makes a little bit of sense. Again, just practice it a few more times. Hopefully that will help. Let me know if you have questions. Now, the question you might have been asking is, why are we trying to make this weird epoxide thing? So it turns out that epoxides are actually pretty good electrophiles, and so they're a good way to get something with an alcohol and be able to also add something else to that carbon that's nearby. So we're going to look at that mechanism. So this is not technically an addition mechanism because it doesn't start with a double bond, but it makes sense hopefully for this section just because we're with the epoxides. And also when we get to the synthesis, it's going to make another way for us to do a cool thing. All right, so what we're going to do for this one is, it's just like an SN2, which we did not that long ago. So the first step is, if it's an SN2, what's the very first step of any SN2? Right? It's going to be the nucleophile attacks. That's always the first step. So it's not a carbocation thing. It's just nucleophile attacks. So if it's an SN2, I'm going to attack the epoxide. It's going to be my electrophile. And this is going to be my strong nucleophile. So I'm going to redraw it with the minus charge, right? So now which side is it going to attack? Before, we always had a leaving group that just had one bond, so we knew exactly where to go. But in epoxide, technically you could attack on either side. So which side is better for SN2? So think, do we want primary, secondary, tertiary, that kind of thing? right? It's going to be the primary side or whichever side is the less steric hindrance, okay? So this one has two different sides. This side has 2 carbons, so it'd be secondary. This one has 3 carbons, so that'd be tertiary. So which side do I want to attack it on? Right, I'm going to attack it on this side on the left. So I'm going to draw my arrow from the negative charge of the nucleophile to the carbon, that's the less sterically hindered one with the epoxide. Then I have to have my leaving group leave. So in this case, my leaving group is just that one bond of the epoxide, not both of them, just one. So it's going to go from the bond to the oxygen to make a minus charge. And then that's the first step. That's all you have to do. So let's draw that product. It's not going to be the final product yet. So we'll draw a product down here. So if we look, now we have the nucleophiles on there and the O- is on there. So I went ahead and drew the O- as a wedge because it should stay the same because it's still attached, right? But which side is the nucleophile going to be on? Is it going to be on the same side as the leaving group or the opposite side of the leaving group? Remember, it's SN2. Right, so it's going to be backside attack, so it's got to switch. So it's going to switch to be a dash because the other one was on the front. Okay, so then I've got my leaving group. What's the last thing I need to get to the product? Just the hydrogen, right? So what do you think that hydrogen is going to come from? Right, we have this H3O+. So the H3O+ is after the semicolon. So before we had some reactions that were 1, 2, and the 1 means you do step 1 and the 2 means you do step 2. The semicolon means you do everything before the semicolon first, and then whenever that step's, quote, done, then you don't like have to work it up or move it or anything. You just add the next thing. And once you add the next thing, then everything's mixed together. You do have to draw that semicolon over the arrow because if you don't, it's saying you'd mix all those things together. And if you mixed all the things over this arrow together without the semicolon, it means that the sodium azide, which is the nucleophile, would mix with the hydrogen and make an acid, which would totally change the product you get from the epoxide. So basically, without the semicolon, the reagents would react and it would get ruined. So I'm going to use the H3O+, and what kind of reaction is going to be the last step? It's going to be an acid base, right? So obviously my acid is going to be the thing with the plus. So I'm going to draw out my hydrogen here, and then it's going to go start my arrow where? Right on the negative charge to the hydrogen, and then break that bond to go to the oxygen with a positive charge. And then that's your product. So this one does have 2 steps, but they're steps you know, right? You know SN2 and you know acid base. The only thing that's different is the epoxide. You have to make a choice at the very beginning of which carbon to attack, but everything else should be stuff you already know. As one final check, let's make sure we understand where all the arrows are doing. So pause the video and I want you to show for each color which arrow is making which either bond or a lone pair / charge, and then see if you can figure out what that is. And make sure you do that for the final product. You don't necessarily have to do it for the middle part. You can if you want to, but definitely do it for the final product. Okay, so pause that and check that. Okay, is this what you got? So if we look, this arrow here made this bond, right, in the product and the intermediate. This one here made the negative charge. So basically it made a lone pair that caused it to have a negative charge on the intermediate. You can't really see it in the product. It's there. It's right here. And then this last one made the bond between the oxygen and the hydrogen. Great. So hopefully that makes sense. Again, if you have questions about any of these mechanisms, you can definitely ask me. I'm happy to help with any mechanism questions. So with that, we're done with our videos for the day. So you're done with addition reactions for the day. Make sure to try the activities on your course website.